Hey, I wanted to go over this example question adding two vectors. And so we're trying to add vector v1 over here, which has a magnitude of 8 meters per second, and it's oriented at an angle of 35 degrees relative to our x-axis. And then vector v2, which is 2.50 meters per second magnitude, and it's pointing straight in the negative y direction. Now, in general, unless we say otherwise, we're always sort of looking at our typical xy axis, where the positive values of x are on this side and the positive values of y are on this side. And so what we're going to want to do with this is we're going to want to take our v1 and break that into what would be the x component of v1 and then the y component of v1. So v1, we'll call it comma y. And then the same thing with v2. Now v2, I'll just go ahead and write it in there now because it's actually a little bit easier than typical ones because it's all in that y direction. So there is no x component to v2. And then its y component would be negative 2.50 meters per second. So these vectors are velocity vectors. And so the way that we're going to typically try to attack adding vectors is by breaking them into their x and y components, or whatever sort of reference frame we have, and then adding up those components. That's going to be our way that we're going to, typically in physics classes, that's how people do it. It's the easiest way most people find to do it. And so the first step is breaking them into components. So for the v2, we've got that. The v1 is going to be a little bit harder. And also, just so you know, so here's the actual answer. So if you want to stop and try to work through it yourself, please feel free. But just so you kind of know ahead of time. But let's go through here and try to figure it out. And so as I said before, so v2 is going to be 0 and then negative 2.50 meters per second. Now for v1, what I'm going to do is I'm going to use my knowledge of right triangles. Okay, and so this here would be my v1, the x component, and this one would be my v1, the y component, as we were talking about before. And so how do I do that? Well, in this case here, again, what we do is we start with our SOHCAHTOA. So that's kind of what I'm going to start with. SOHCAHTOA. Now, so cosine of 35 is going to be the ka, and so it's adjacent over hypotenuse. And so in our particular example, cosine of 35, the adjacent side is going to be this one here. So it's v1 in the x direction, and my hypotenuse is the 8 meters per second. And so if I go through and solve that, I get one of my components, v1x equals 8 meters per second times cosine 35. Now let's look at this for a second. So the way I've been doing this is sort of starting with these fundamental cosines and kind of working down. Now eventually what you'll want to do is you'll get to the point where maybe you can do it a little bit faster and kind of recognize. And so the way that I like to think about this when we're doing this is say, okay, so we have this triangle, and so this is my adjacent side. If I know the hypotenuse, then to find the magnitude of the adjacent side, it's going to be the hypotenuse times the cosine function, because cosine gives us adjacent. All right, and if I do the other side over here, I get sine 35 equals opposite of over hypotenuse. That's the SO, right? And so again, if I look at my picture, the opposite side would be the v1 in the y direction. Again, my hypotenuse is 8 meters per second. And so when I get this, v1y, it comes out to be 8 meters per second times sine 35, right? And so sort of our rules of thumb are, when you have a right triangle, if you know the hypotenuse, then multiplying the hypotenuse length times the cosine of the angle, right, gives you the side that's adjacent, which is the side that's touching the angle. That's kind of how I, sort of math speak for the side that's sort of touching that angle. And opposite is going to be the sine function, and that's the side opposite that. So here, the angle is the one right here. Now again, they could give you the angle over here, so you got to be careful, right? Like I was saying or I've said before, a lot of times the x component will be the cosine function, but not all the time. It depends entirely on which angle that you've picked. You can even be kind of sneaky, right? Say, for instance, that this problem gave you the beta angle over here. And you're like, well, I don't like that. You can always just subtract and find what the angle would be over here, because we know that how the angles inside here have to add up to 90. So a lot of little tricks you can do. And so I'm kind of starting fundamentally with the cosine and the sine and building up for that. But you'll probably get to the point throughout the course where you kind of can jump right to here. But you got to be careful when you do that. Now, when I plugged these into my calculator, for this one I got 6.55 meters per second. And for this one, I got 4.58 meters per second. Again, that's taking 8 times the sine function and 8 times the cosine. And so now if I want to add up my V1 vector, this would be 6.55 meters per second and then 4.58 meters per second. And these are both positive. Again, like we said before, unless we state otherwise, we're typically going to be using, I will typically be using an XY coordinate system like this here. And so the vector V1 is in the positive X and the positive Y. So both of these are positive. The only time we had to think about negative was for this V2. Now, the whole reason we write the vectors this way, right, is so that then the V total, the addition of them, you can just add up the sides, right? So I can say 0 plus 6.55, so my resultant vector here will be 6.55 meters per second, because that's 6.55 plus 0, and then 4.58 minus 2.50, so that gives me 2.08 meters per second there. All right, so in some sense, we're done right here, right? We've calculated the total vector. However, the person who wrote this question wanted you to give the answer in magnitude and direction format. Okay, I guess they're a jerk or whatever. Who knows? Okay, but that's okay. We can handle that. So the way that I typically would handle this is I would just make another right triangle. So I'd say, okay, so my V total has an X component of 6.55 meters per second and a Y component of 2.8 meters per second. And so what we've done is we've just made another right triangle. Okay, and what we can do is use Pythagorean's theorem to figure out the hypotenuse. And so when I did that, I got 6.8 meters per second. That's great. The last thing we need to do is find this angle here. And so the angle, the problem told you to find the angle above the x-axis. And so in our picture here, this would be the angle that we would be looking for. And so what I would do there is, for the last part, I'd say tangent theta. Again, from my rules, that would be the TOA. So it's O over A. And so opposite side would be the 2.08 meters per second. Adjacent side would be the 6.55 meters per second. Again, the meters per second cancel. And I do my fancy arc tangent. So I would take the tangent -1, or arc tangent, depending on what your calculator says, 2.08 divided by 6.55. And when I did that, I got an angle of about 17.6 degrees. Now, this is a thing here. You want your calculator to be set on degrees, so that could throw you off. But typically, if you have it set on radians, you get some kind of way different answer, because radians are significantly different than the degrees. Okay, so here's how I got that answer. Okay, and so then just to sort of add on to that, we can discuss, why am I allowed to do this? Why does this procedure work? And so here's how I like to think about it. So if we have two vectors in the same direction, right, it's not too bad to add them up. So say I've got two vectors. Here's one magnitude of 5, one magnitude of 6. They're in the same direction. So what I do is I put them head to tail of each other like this here, and I get the total magnitude being 11. All right, so when they're in the same direction, it's easier to deal with them. However, if you've got two vectors like this, so suppose I got two vectors that aren't in the same direction, okay, what do I do? Well, our whole principle here is to back up and use essentially our right triangle geometry to figure trigonometry to figure this out. And so what I do is I break these into their x and y parts like this. And what I'm doing is I'm breaking them into parts that are parallel with each other. And so then to get sort of the grand total, I put the two blue ones, they're two what you might want to call x components, right? Again, unless I say otherwise, I'm using this as my x and that as my y. And then adding together our two y components to find the new magnitude. And so that's what we're doing, in a geometrical sense when we break those vectors down like that. Thank you.